In this video, we will learn about multiplication operations between vectors. In contrast with algebraic multiplication, there are two ways we can perform the product between two vectors, which are the dot and the cross products, which gives us a scalar and a vector product respectively. If we have two non-parallel vectors, vector A and vector B, with an angle of theta in between them, the product of the magnitude of vector A, which means the length of vector A, multiplied by the length of the component of vector B, which is parallel to vector A, that means this length over here, will give us the dot product of the vectors A and B. If we are given the components of vectors A and B, we can calculate the dot product using this formula over here, where we will take the product of the terms of each row, A1 times B1, A2 times B2, A3 times B3, and we will add them up. For example, if I have the vectors 1, 2, 3 performing a dot product with the vector 4, 5, 6, we can evaluate this dot product by simply saying that it is equals to 1 multiplied by 4 plus 2 multiplied by 5 plus 3 multiplied by 6, and therefore this gives us 32. Some properties of the dot product are: number one, A dot A equals to mod A square. This is because we know that A dot A can be written as mod A multiplied by mod A cosine 0. Since the angle between A and A, they must be 0. And cosine 0 gives us 1, and therefore this becomes mod A square. And this is how we arrive at the first property. Number two, if we have two vectors that are mutually perpendicular, their product will be 0. This is because we have now A dot B equals to mod A mod B cosine 90 degrees. And we know that cosine 90 gives us 0, and therefore the dot product of two vectors that are mutually perpendicular is always going to be 0. Number three, we have the commutative property. That means A dot B is equals to B dot A, and they are interchangeable. Number four, we have the distributive law, meaning that we can expand the brackets that contain vectors like how we expand normal algebra. In example 1, we are going to make use of some of the properties of the dot product. So we have a triangle OAB such that angle OAB is 90 degrees. So I have this right angle triangle OAB, and the angle A is 90 degrees. And I want to show that A dot B is actually equals to mod A square. So how do I show it? Now recall that if you have vectors that are mutually perpendicular, their dot product is always equals to 0. And therefore, I can say that AO must be perpendicular to AB, which means that vector AO, if I perform a dot product with vector AB, it must be equals to 0. Now, let me write AO and AB in terms of small a and small b, and this gives me negative A dot product with B minus A, it must be equals to 0. Now let's expand this. We will end up with negative A dot B plus mod A square equals to 0. And this mod A square is because I have A dot A. And therefore, from here, if I rearrange this equation, I will end up with A dot B equals to mod A square. And thus, I have shown the relationship. We can make use of the dot product to determine the angle between two vectors. However, we should note that when calculating the angles using dot product, both vectors should either be pointing outwards or pointing inwards, as we can see from the diagram. Rewriting the formula for the dot product, we can show that the angle theta between two vectors will be equals to the inverse cosine of A dot B over mod A mod B. Now, if A dot B over mod A mod B is more than 0, this will give us a theta that is acute, that means between 0 to 90 degrees. If, however, A dot B over mod A mod B is negative, the angle that we get will be an obtuse angle between 90 degrees to 180 degrees. Therefore, if the question asks us to find the acute angle between two vectors or two lines, we will put a pair of modulus outside this term to make sure that it is always positive and thus give us an acute angle. In example 2, we are given 3 points A, B, and C and asked to find out what's the angle of CAB. So if we draw the diagram out, I have C, A, B, and I know their respective coordinates as well. And I'm interested to find out what's this angle theta. Therefore, I will first have to find out the two vectors AC and AB. AC will be equals to OC minus OA, which I can calculate to give me minus 2, minus 1, 0. And AB will be equals to OB minus OA, which I can calculate to be 1 minus 3, 1. And therefore, the angle between them will be theta equals to cos inverse negative 2, negative 1, 0 dot with 1 minus 3, 1 over mod of minus 2, minus 1, 0 mod of 1 minus 3, 1, which is equals to cos inverse of 1 over square root 5 square root 11, and on pressing the calculator, this gives us an angle of 82.3 degrees. The direction cosines alpha, beta, and gamma of a vector are simply the cosines of the angles that the vector make with the x, y, and z axis respectively. For vector PQR, we can calculate its direction cosines using the following formula. And this formula can easily be derived using the dot product. So I will just show you using one of them. For example, if I'm interested to find out what is alpha, I know that alpha is equals to cosine of A, and A is the angle that vector PQR makes with the x-axis. And therefore, I can write it as vector PQR dot product with 1, 0, 0. Since the vector 1, 0, 0 is going to be parallel to the x-axis, divided by mod of PQR and mod of 1, 0, 0. And on evaluation, the numerator becomes a P and the denominator becomes square root of P square plus Q square plus R square. And that is how I derive the formula for the direction cosine, and you can do so similarly to obtain beta and gamma. In example 3, we are now asked to evaluate the direction cosines of vector AB given that we know the points A and B. And so the first thing we have to do now is to obtain vector AB. So vector AB will be equals to 3, 1, 2 minus 2, negative 1, 4, which gives us 1, 2, negative 2. And therefore, for the direction cosines, we just have to apply the formula that we have learned earlier. Alpha will be equals to 1 over square root of 1 square plus 2 square plus negative 2 square, which becomes 1/3. Likewise, beta will become 2 over 3 and gamma will become negative 2 over 3. Next, we look at the cross product. As opposed to the dot product, the cross product gives us a vector instead of a scalar. Graphically, the product of A cross B is the vector that is perpendicular to both vectors A and B. So this is perpendicular, this is perpendicular as well. By definition, the product of A cross B is defined as mod A mod B sine theta multiplied by n cap. And n cap over here is a unit vector that is in the direction of the resulting vector, which is the normal vector since it is perpendicular to both the original vectors. So you can think of this as n equals to mod n times n cap, where n is a cross b, mod n is ab sine theta, and n cap is the unit normal vector. Of course, with the unit normal vector, this form is not very useful, and what we want to do is to get rid of the unit normal vector by simply applying a pair of modulus, and thus we obtain this second form over here. To calculate the cross product between two vectors, we have to be familiar with finding the determinant of a 2 by 2 matrix. Say if I have a matrix ABCD like this, finding the determinant be the same as saying finding the modulus of a matrix. It gives me AD minus BC, where I take the downward multiplying product subtracted by the upward multiplying product. So for a cross product, we will perform this determinant finding process 3 times. To find out the first component in our resulting vector, what we have to do is to simply cover up the first row and find out the determinant of the remaining 4 terms. Likewise, to find out the second term in our product, we will have to cover up the second row and find out the remaining determinant of the 4 terms. And likewise, for the third term, we cover up the third row and find out the determinant of the remaining 4 terms. However, do note that for the second term, we have to add a minus sign over here. Some properties of the cross product are, number 1, A cross A equals to 0. This is because the angle between the both of them is 0. So I have A cross A equals to mod A sine theta multiplied by n cap. And since sine theta is equals to 0, I will end up with 0. But do take note that since it is a vector over here, this 0 shouldn't be just a 0, but instead it should be a 0 vector, and we represent it by putting a squiggly at the bottom. Number 2, the cross product is not commutative like in a dot product. This is because the cross product is a vector, and if we reverse A and B, the direction of the resulting vector will be opposite. Thus, A cross B is equals to negative of B cross A. Number 3, the cross product follows distributive laws, which means that we can expand brackets like in normal algebra. One useful application of the cross product is that we can use it to find out the area of a triangle or a parallelogram if we know the two vectors that make up these shapes. For a triangle that is made up of vectors A and B, like in this diagram, recall that we can find out the area using the formula half AB sine C, where A and B are the lengths of the sides of the triangle and C is the angle subtended in between these two lines. So we can write the area as half mod A times mod B times sine theta in this case. And also, since I have mod A mod B sine theta, this is equals to mod of A cross B as we have learned earlier. And therefore, the area of this triangle can be simply found using half of mod A cross B. Similarly, for a parallelogram that is formed using vectors A and B, the area is simply 2 times the area of a triangle, and thus it is simply the mod of A cross B. In example 4, we are going to find out the area of triangle ABC, where the coordinates of A, B, and C are given. So I have this triangle over here, point A, point B, and point C. And if I want to find out the area of this triangle, I can use vector AB and vector AC and do a cross product between them. And this will first require me to find out the two vectors. Vector AB will be equals to OB minus OA, which is equals to 1, negative 3, and 1. And AC will be OC minus OA, which gives us 2, -1, 0. And therefore, the area will be equals to half of mod AB cross AC, which is equals to half mod 1, -3, 1 cross with 2, -1, 0. And if we perform the cross product, we will end up with 1, 2, 5. And now if we take the modulus of this vector, we will yield half square root 30 square units, which is the area of this triangle. How we can derive this expression is exactly the same as how we arrive at the formula for the length of projection. In example 5, we are asked to find the length of projection of B onto A, given that we know A dot B equals to mod A square, and that the length of OA and OB are 3 and 5 respectively. So how do we find out this length of projection? We are going to start with the formula for finding the length of projection, which is mod of B dot A cap, since it is the projection of B onto A. Let's rewrite this expression slightly. This gives me B dot A over mod A, since A cap is the same as A over mod A. And I'm going to rewrite this further as A dot B over mod A. This is because A dot B is equals to B dot A in what we have learned earlier for the properties of the dot product. Now, A dot B, we know that it is equals to mod A square as given in the question, which gives us mod A square divided by mod A. And if we reduce this, we will end up with just mod A, and this gives us 3. And therefore, the length of projection of B onto A is simply 3 units. In example 6, we are given vectors A and B and asked to find out the lengths of projection and rejection, and also the projection vector of A onto B. So let's find out the length of projection of A onto B first. The length of projection will be equals to mod of A dot B cap, which is going to be mod of 134 dot product with 608 divided by the modulus of 608, which is modulus of vector B. And if we evaluate this, we will end up with 3.8. And for the length of rejection, it will be mod of A cross B cap, which is the mod of 134 cross with 608 divided by mod of 608, which gives us mod of 24, 16, negative 18 divided by 10, and therefore we get 3.4. And finally, for the vector of projection of A onto B, we can write it as PROJ, projection of vector A onto vector B, like this, equals to 3.8, which is the length of projection, multiplied by B cap. So we have 3.8 multiplied by 608 divided by the modulus of B, which is 10, and therefore we end up with 0.38 times of 608, and this is the projection vector of A onto B.